Welcome everybody. This is the data ingestion video of the large-scale machine learning portion of ML Expert. In general, when we create these large-scale machine learning systems, we're going to have some form of ingestion. What this means is we want to get data into our system so that we can do some sort of analysis on it and eventually use that data to run machine learning algorithms. So the first area that we're going to cover is something called streaming ingestion. Streaming ingestion usually involves things like clickstreams, change data captures, and live video feeds. We'll start with clickstream. Clickstream keeps track of what the user interactions are with some particular interface. This could be a mobile app, could be a voice assistant, and it could even be a desktop. Now, this clickstream will potentially have to manage millions of events or interactions per second coming from all of the users for a single particular interface. So what does the clickstream actually keep track of? Well, in most cases, the clickstream is going to have a record per event, and that event is going to have some date and time in which the event or interaction occurred. It'll have a user agent that'll tell us what type of browser were they using, were they on the mobile app, were they using the desktop version of the web app, things like that. Next up, if they're signed in or logged in, they'll have a user ID associated with their particular click event. We'll also want to capture the request details. What page were they looking at, and where did they click on that page? We'll also like to keep track of something called a session ID, mostly in the case that they're not logged in. So if your site doesn't require people to log in, we can actually associate some sort of cookie with their device such that we can still keep track of their interactions even though we don't have a specific user ID for them. A couple of other things that we could keep track of is where they are in terms of their IP address, as well as how they found our website. Did they go through Google or Facebook, something like that. So today we'll be talking about two tools that we can use to help us sort through these potentially millions of records every second. We'll be talking about Kafka and Kinesis. Kafka is an open source Apache project, and Kinesis is a fully managed AWS service. You may also hear these tools be referred to as PubSub or Publish and Subscribe. Kafka allows us to create brokers, and these brokers manage the interactions between some producers and some consumer. So here, our producer will be some sort of clickstream logs. These are the clickstream records that we talked about earlier. These clickstream logs will be sent to particular Kafka topics, and they will have partitions on the broker such that the consumers, in our case we'll talk more about storage later, but that the consumers can consume from these brokers to now store these clickstream logs. So what happens if our clickstream logs come in at a far faster rate than a single broker could handle? In that case, we're going to have a broker cluster. Here, every single clickstream log will be sent to a particular partition, and one of these brokers in the broker cluster will be assigned to be the partition leader. And all the partition leader does is make sure that all of the reads and writes go through that particular partition, and it also replicates the partition across other brokers in the broker cluster. In order to manage all of these brokers in the broker cluster, Zookeeper handles the management of the leader of this broker cluster, such that if one of the brokers is a leader and it goes down, it can then substitute in another broker in this cluster such that it can take its place. It'll also keep track of different topics for each configuration. So for instance, if we had clickstreams coming from a home page, that could be one topic. If we had clickstreams coming from a search page, then that would be another topic that Zookeeper could manage for our brokers. So in general, Kafka will give us this scalability aspect such that we can add more and more brokers to this broker cluster. That allows us to support potentially millions of clickstream logs or records coming in. And to manage all of the brokers in this cluster, we can use Zookeeper to keep track of which broker is assigned to which partition and how to manage those replicas in the case that a broker goes down and a broker needs to come back up to take its place. Next up, Kinesis is another way to accomplish effectively the same thing. We'll have our clickstream logs or records coming in this way. Kinesis actually has shards instead of partitions, and the number of shards present can scale up just in the case as our brokers did with Kafka. Again, we have the same consumer pattern over here, such that some storage layer would eventually receive these clickstream logs. Now, in our example, we use clickstream logs here, or these clickstream records, but in reality, they could be anything that has the streaming ingestion aspect of it. So we could have web crawlers crawling the web and incrementally sending data to these shards. We could have some RSS feed that we're listening to that could be collected and sent to these shards. And it could even be another storage instance, such as a database. How we ingest changes to databases is a process called change data capture. So let's say that we have a database, and it's keeping track of who, in terms of a user ID, is subscribed to Netflix. So effectively, a row in this database would be keyed on some user ID, and the value would be, is this user ID actively subscribed to Netflix? And also, we want to know their renewal date. So if we're going to build a machine learning model and we wanted to predict whether someone will or will not renew, we care about their current state of their subscription because they can't cancel if they're already canceled. And we also care about the previous status of their membership so that we can see when did user X cancel and tie that to some service usage before they canceled. So here the hypothesis is that maybe their usages have gone down before they decided to cancel. So if we wanted to model this, we couldn't just look at that database, which keeps track of whether a user is currently or not currently subscribed to Netflix. We actually need a history. This history will tell us when did they unsubscribe or when did they subscribe. So here we're going to use a tool called change data capture. What this will do is it will tap into a log of changes to a particular row in some database table. It will send these change logs to the streaming tools that we talked about, Kafka or Kinesis. So now our producers will actually be these different storage instances. Any one of these storage instances could keep track of perhaps the actively subscribed users to some service. Every single time that a row in a table, say of actively subscribed users, is updated, well, we can actually look at the change logs associated with these databases and send that information to our broker. In this case, this would be Kafka. And now our consumers could store this change in usage or the change in actively subscribed users such that we could build a model to predict which users will and will not renew. So you may hear this paradigm of online transaction processing, that's OLTP, and online analytical processing, OLAP. A system like this would keep track of who is actively subscribed, such that if you log in, we know to grant you some particular membership benefit. This over here will keep track of when you subscribed or when you unsubscribed. So now that we've gone over change data capture, we're going to finish with live video. So live video could mean ingesting video content from traffic cameras, security cameras, or video streaming services. An example is HLS, which is HTTP live stream. Basically what it does is it takes an MP4, chops it up into segments, and sends out those segments over HTTP. So how would this look in terms of our producer, broker, and consumer paradigm that we've talked about before? Well, now we would have different video cameras. These could actually be maybe not 1930s video cameras, but they would actually be surveillance cameras, something like that. These cameras would be sent to some collector. Effectively, we need this layer here to disassemble the video into some frame-by-frame representation. And this collector, frame by frame, could compress that frame to save cost of transporting it over to the broker, but it would effectively just ship these frames over to the broker such that they could be then consumed and stored. So that would be how live video gets ingested such that we could use live video for some maybe computer vision algorithm that we would later feed into a convolutional neural network. So now that we've covered streaming ingestion, let's go ahead and move on to batch ingestion. Batch ingestion can take place when we want a periodic snapshot of some database. This is also useful as a first step for when we want to onboard a database before we use change data capture on it. This allows our storage system to be fully up to date with the database contents before we start keeping track of all the changes to that particular database. So here are the technologies that we can use to transfer the data to some particular database instance into some storage layer that we want to use for analytics. This is very similar to change data capture, except that we're not waiting for a change anymore. We're simply dumping all of the data that's in these databases into our storage layer. So in general, the considerations that we need to take when we're talking about ingestion is going to be the size of the individual data. So an example of something with a smaller size would be the clickstream. Every single clickstream record is maybe just a map of a few keys and a few values. However, the size of the individual data is going to be far larger if we're shipping entire video frames to the brokers. So that's one consideration that we got to have when we're talking about ingestion. Another factor we have to consider is the rate at which these records come into the brokers. Will there be a million records per month, say maybe in the case of a subscriptions table? Or will there be a million records per second, such as a clickstream? We also have to consider what form of data will be transmitted to our brokers such that our brokers can handle this data. Finally, we need to talk about high availability and fault tolerance, such that if a broker goes down, then another broker can easily come and take its place without any loss of data. As well, to avoid networking problems, you'll likely want to replicate your partition data, say in Kafka, across different availability zones. This effectively means putting those brokers in different data centers. Now, let's go ahead and see a very basic example of a clickstream. So the first thing we'll do is go ahead and look at the Zookeeper properties that we have. We're going to give it a temp directory to work with. We're going to give it a particular port to run on. And then right now the max client connections will be 0. This is the default configuration provided by Apache. So we're not going to change anything here. Now that we've seen the properties, let's go ahead and launch it. So here we're just going to run the script zookeeper server start. This comes default with the Kafka version that I have installed. So here we're just starting the zookeeper server while handing it the zookeeper properties file that we just looked at. So this will start zookeeper. Now let's go ahead and launch the broker itself. So here we'll launch the Kafka broker. That as well is going to have its own properties file. And this is also going to be the default Kafka broker file provided by the default installation of Kafka. Now that we've seen the server properties, let's go ahead and launch it. Here we're just going to use Kafka server start, which is provided by the default installation of Kafka itself. So now we have started up our Kafka broker. Now, remember, in production, we would actually spin up several Zookeeper instances and several brokers, but since this is just locally being tested here, we'll go ahead and stick with one each. Finally, we need to set up a producer. So in that case, we're going to create a simple web app, which will have a clickstream being produced from that simple web app and send it to the Kafka broker to be later consumed. So let's go ahead and look at a simple server file that we have. Flask is a lightweight web framework, and all we do is we start the Flask app, we connect the Flask app to our Kafka broker, which is running locally on port 9092. We have a home page that has a search bar, and the simple web page takes in a text to search for, and it has a submit button. On that submit button, we're going to call this function here and forward it to this path. This path will then form our clickstream record, which here we just called message. And this message is going to have the request path, which is here search. It'll have the search term that we searched for in the home page search bar. It will also track our user ID, which here I've just fixed it to some ID. It'll also contain our IP address, which I've also fixed. And finally, we have the date, which will just be recorded as whatever date the event took place. We're going to print that message out to the console just for debugging purposes. And finally, we'll send this message to the Kafka broker in the form of bytes. And as well, our result of the search right now is nothing, so we'll just say, sorry, no results yet. Here you'll notice that as a producer, we're sending this message to the Kafka broker under this particular ID here. This ID, ML-Expert, is our topic. In addition to the steps that we've already taken by spinning up Zookeeper and spinning up the Kafka broker, you would normally have to create your topic with another command. In our case, I've already created the topic ML-Expert, so the topic is already there. Now we can reference the topic in this code here, and it will know where to send this message to the broker. All right, let's go ahead and launch this server. This command will start our Flask server, and now all we have to do is navigate to whatever host this is on port 5000. So when we do that, we get our simple page here. So again, we just have a search term bar and a submit button. And the idea is that when we type in a search term here and click submit, the web page will send a message to the Kafka broker that we spun up earlier. So if we do type in a search term here and click submit, and that message does go to the broker, how do we know it actually went to the broker? Well, we can create a simple Kafka consumer, which will just print results to our terminal. So let's do that. This command, which is included with the default installation of Kafka, will begin consuming from the ML-Expert topic, which our web page is sending the contents to. And here we're just indicating where the broker is located, so that's on port 9092, and also Zookeeper. Let's go ahead and run this. And now, if we navigate back to our web page, I can have hello be the search term. And again, our results will be sorry, no results yet. That's what was in the original code that we looked at. And if we navigate back to our simple consumer that we just created, we'll see that our message did come through to the consumer. What this means is that the web page did successfully send the message to our broker, and we had a consumer consume this particular clickstream record. Now, in reality, millions of these could be sent per second. This is just to showcase how to get something very simple set up quickly. So in total, we've went over the streaming ingestion process, and that covered things such as clickstreams, change data captures, or live video. And as well, we went over batch ingestion, which incorporates the entirety of the database and not just the changes associated to them. That concludes our data ingestion video in the large-scale machine learning section of ML-Expert. Thanks for watching, and we'll see you next time.